Okay, so for each of these, the first thing we have to do is figure out how big, what each division stands for, how big each division is. So our first one, we'll go from 1 milliliter to 2 here. 2 milliliters minus 1 milliliter is just 1 milliliter. And we count 10 spaces in between. So that is 0.1 milliliter per space. So we're starting here at 4.1.2 milliliters. The second one, from 0.5 to 1, so that's 1 milliliter minus 0.5 milliliters is a difference of 0.5 milliliters divided by 5, 10, 15, 20 spaces between them. That is 0.025 milliliters per space. That's going to be awkward to count. But what that's telling us is every 4 spaces, if I multiplied that by 4, that's 1/10. So every 4 spaces is 1/10. So if that's 0.5, 1, 2, 3, 4, that's 0.6. 1, 2, 3, 4, that's 0.7. Now, lucky for us, it just happened to come out right on the 10th. So 0.7 milliliters. Actually, I technically should write that down as 0.70 milliliters. Maybe even 0.00. But you might wonder, well, what's the difference between 0.7 and 0.70? Mathematically, they're the same. There's an implied difference there. Having that 0 on there is saying we did measure this down to the nearest 100th of a milliliter, and it just happened to be closer to 70. This is saying, yeah, we only measured it the nearest 10th of a milliliter. That's not really a scope of this course, talking about measurement and errors, but the way you write down that measurement, it is implied. It's more important that you don't just tack a 0 on. It would be more important here that we don't say 4.20 milliliters, because that 0 is saying that we measured it more precisely than we did. So avoid doing that. Okay, it looks like you guys have the syringes down okay. So we're going to take a look at our next step. Before we talk about the dosage formula, I do want you, if you have your book handy, to look at the top of page 150. What's on the top of page 150 is our abbreviations. And I'm not going to specifically test you on any of the abbreviations. It's not going to be on a test or anything like that where you have to identify them. And I'm not going to go through all of them with you. But I wanted to point this page out to you because you may want to mark it or at least look it over and get familiar with them. Because as you're doing the homework, you are going to see these abbreviations used. If you see Q6H, you need to know that that means every 6 hours. Or if you see QID, you need to know that means 4 times a day. Because now that we're moving into actually calculating the size of dosages, and one of the things we're going to look at is it a safe dose? Often your safe doses are given in the amount of medication a person can receive per day. Knowing how many times per day that it's given is going to allow you to do that calculation to see if it is a safe amount of medication. Also, of course here, being familiar with this might avoid confusion if you see it printed as Q6H and you are told, hey, do it 4 times a day. You have to be able to identify that that is the same thing. Every 6 hours and 4 times a day are the same frequency. Now for like this course, like IM and IV, intermuscular or intravenous, really don't have anything to do with the math. I mean, from your side of it, that's how you're going to administer the medication. That's going to be important in the field and clinicals especially, but in this course, that really doesn't affect whether it's orally or intramuscular or intravenously, doesn't affect our calculations. But again, for you, it might change how you prep it in practice, and it definitely changes how you're going to administer it. So like I said, bookmark that page or do something so you can come back to it so you are familiar with those abbreviations, because they do affect how we do our calculations. That's all I'm going to say about the abbreviations. As they come up, we will use them and we'll identify them. But our next step, we are going to talk about the dosage calculation formula. As we look at dosage calculations, we are going to actually look at 3 methods of calculating dosages. One is this formula. The formula has a couple of weaknesses. One, it's a little bit clumsy. For a lot of cases, for some problems, you'd have to repeat it 2, 3, sometimes even 4 times to get from where you're starting to where you need to go. The other big weakness is you got to memorize it. It's something you got to memorize. It's just a little bit clumsy. The strength of it, of course, is if you have it memorized, you just plug in numbers and crank them out. The second method we're going to use, that we're going to look at, is a proportion method. There are definitely certain cases where the proportion method is very simple to use, especially if you have a dosage given as like 6 grams or 6 milligrams per kilogram of weight or something like that. I'm using the proportion method is very quick to figure out what is the dosage to administer to that patient. But again, there are some cases where that proportion would have to be repeated 3 or 4 times to get from one position to the next, the beginning of the problem to the end. Third, we're going to have dimensional analysis. This is what we looked at the end of the last unit, where we had the units in fractions and we cross-canceled as we went through them. This, to me, is the most useful method, because even if you're not sure what to do with the medications, the units and the labels on the medications and the things you're given can actually tell you how to do the calculation. For the most part, to me, the simplest way of doing it is a mixture of dimensional analysis and proportions, where the proportion is used in a very, very specific different situations. Like I said, where you're given, okay, so many milligrams per kilogram of mass, or so many milligrams or milliliters per square meter of body surface area, situations like that. Dimensional analysis is stronger for almost all other situations, and often we use both in the same problem. As I had mentioned, the formula is good if you just want to memorize and crank stuff through, but there are going to be a lot of situations where it gets really clumsy. So let's start out looking at the formula. I'm going to kind of go through these from my least favorite to my most favorite. The formula is D over H times V equals A, where D is the desired amount. That is the amount of medication that you desire the patient to receive. Here's another one of the things I don't like necessarily about this formula. H and V can be kind of confusing. H is called the on-hand dosage. It's the dosage on hand. It's how much is in each unit of the medication that you have. V is the vehicle. The vehicle is what carries the medication into the patient. More specifically, it is what carries the on-hand dosage to the patient. So if you're struggling to figure out what the on-hand dosage is, look at the vehicle. The two of them are pretty much always linked together. And then, of course, A is what we're going to administer to the patient. So let's look at some examples. Our doctor orders 600 milligrams of ibuprofen. You look at your bottle. The label on the bottle says 200 milligram tablets. So trying to sort through this formula, what is D? D is the desired dose, or often the ordered amount. H and V come from the label on the bottle. Let me show you what I mean. So D is 600 milligrams. H, or on-hand dose, as I said, the on-hand dose and the vehicle come from the label on the bottle. Whatever goes down here for the on-hand dose must have the same units as the desired dose. So whatever goes down there has to be milligrams. So looking at the label on the bottle, what's on the label that's in milligrams? 200. So 200 milligrams is our on-hand dose. According to the label, what carries that 200 milligrams into the patient? This is a little tricky. It's very subtle. 200 milligram tablets. One tablet carries 200 milligrams into the patient. So a tablet, or one tablet, is our vehicle. So the milligrams divide out. Those units have to be the same so that they always cancel out. 600 divided by 200 is 3 times one tablet gives us 3 tablets. So we would administer 3 tablets to that patient. Seems a little bit forced, doesn't it? Let's take a look at another example, a little bit different situation. Let's say that you are ordered, the doctor orders 50 milligrams of medication. Label on the bottle says 5 milligrams, 5 milligrams and 2 milliliters. Often the label will say the medication is constituted to 5 milligrams and 2 milliliters. So anyway, what is D here? My desired dose. 50 is what the doctor orders. So it's 50 milligrams. Now remember, both my on-hand dose and my vehicle come off the label. So I have 5 milligrams and 2 milliliters. Which one goes underneath the 50? 5, yes. Remember, what goes down here for the on-hand dose must have the same units as the desired dose. So 5 milligrams has to go there because it's milligrams, which makes my vehicle 2 milliliters. So what that is telling us is every 5 milligrams of medication is carried into the patient or into the body in 2 milliliters of that fluid. So now we calculate. Milligrams cancel out. 50 divided by 5 is 10 times the 2 milliliters. 10 times 2 milliliters is 20 milliliters. So we would administer 20 milliliters of that medication to our patient. So let's say we have an order for 1,000 milligrams of medication. Our label (400 milligrams scored tablets). Why did I put scored in there? What does scored mean? Yeah. A scored tablet means it has a notch basically in the middle so that you can chop it in half or break it in half to give them half a tablet. We try to never round to anything less than half of a tablet. So what is our D, our desired dose? 1,000 milligrams, what's ordered by our doctor. Our on-hand dose off the label, of course, has to have milligrams. So that'd be 400 milligrams. What carries that into the patient? Just a tablet. So once again, milligrams will cancel out. 1,000 divided by 400 is 2.5. Times our one tablet is 2.5 tablets. So 2.5 or 2.5 tablets is given to that patient. So let's say we have an order for 700 milligrams. Our label is 200 milligram capsules. Tell me what to do. Okay, so 700 milligrams is our desired. You said over 200. That's our on hand. Times one capsule. So the milligrams cancel. 700 over 200 is 3.5. 3.5 times one capsule is 3.5 capsules. Not necessarily a math question, but anybody see a problem with 3.5 capsules? Capsules can't be divided, can they? In that case, since you can't cut them in half, you have to do one of two things. You're either going to round down to 3 capsules, up to 4 capsules, or you're going to go check to see if you can find something with a different size capsule so you can get closer to that dose. So let's say we have an order for 800 milligrams, and our label is 300 milligrams scored tablets again. In your notes, quickly go through, find out what the dosage you would administer would be. So we have 800 milligrams over 300 milligrams times 1 tablet. As we divide this out, milligrams cancel. 800 over 300 is 2.67 times 1 tablet. How many of you got to 2.67 tablets? Show of hands. Most of us. Good. Now that we're there, these are scored tablets, which means we can go to the nearest half a tablet. So looking at this, if we are told it's okay to round it to the nearest half tablet, if you're looking at 2 tablets, oops, 3 or 4, what are we closest to here? Well, 2.67 is going to be between 2.5 and 3. We're somewhere in there. It is closest to 2.5 tablets. So we would administer 2.5 tablets of that medication. Now again, that's only because we are told it's okay to round to the nearest half tablet. So let's say we are ordered to administer 400 milligrams. Our label is 50 milligrams in 2 milliliters. In your notes, find out how much you administer to the patient quick. This will be 400 milligrams over 50 milligrams. What goes in as our vehicle? 2 milliliters. Yeah, the 50 milligrams in our on-hand dose gets carried through the 2 milliliters to get to the patient. Milligrams cancel. 400 divided by 50 is 8 times 2 milliliters. We administer 16 milliliters. Any questions? Okay. Now I want to expose you to the other 2 methods of calculating dosages before we finish up for the day, so that you guys have a week to think about what method you prefer before we polish them up next week. So let's look at a proportion method. If we're looking at the proportion method, we're going to look at our label with our on-hand dose over our vehicle. And on the other side, we're going to have our doctor's orders or desired dose over our administered dose. So what we're trying to administer is right here. You might recognize this formula from test 2. It was one of the formulas we were asked to rearrange. I think you were asked to solve it for A. If I were to solve this for A, it's a proportion, by the way. If there was numbers in here and I was missing this spot, I would cross multiply and divide. D times D and divide by H. In fact, I'm going to write it like this. D times V divided by H. Does that look familiar at all? I mean, it's formatted a little, not really sloppy. It's formatted a little different. D times V is on top divided by H here. On here it's D over H times V, but it's still D is multiplied by V and divided by H. It is the same as our dosage calculation formula. It's just setting it up in a proportion. So let's look at some of our examples we've seen so far and how they would fit into a proportion. So let's say our doctor's order is for 700 milligrams of a medication. And our label says 200 milligrams scored tablets. So we set up as our on hand over our vehicle. So our on hand is 200 milligrams over 1 tablet. So the first ratio is from our label. Our second ratio is easy to set up, because whatever goes on top here has to have the same units as what's on top over here. This has to be milligrams. Whatever goes on bottom here has to have the same units as what's on bottom over here. So this has to be tablets. So I look at my order and it says 700 milligrams. So where does that have to go? Has to go on top. And we could look back up here and see that is our desired dose. The desired dose goes on top, but we don't need to do that. That's one of the nice things about using the proportion method is all we do is we write down here what the label is telling us. Then in the other ratio, we just match up the units. So we cross multiply and divide. 1 tablet times 700 milligrams is 700. Divided by 2 is 3.5. So if we have an order for 50 milligrams, and our label says that our medication is constituted to 5 milligrams in 2 milliliters. Again, we start with what's on the label. The label is 5 milligrams in 2 milliliters. What goes on the other side has to match up. This has to be milligrams. This now has to be milliliters, has to match that unit. Now we see the doctor's orders of 50 milligrams. That's going to go there. So we can cross multiply and divide. 2 milliliters times 50 milligrams is 100. Divided by 5 is going to give us 20. If I want to look at the units and do the dimensional analysis here, I can. This is 2 milliliters times 50 milligrams. That is technically 2 times 50 is 100. Multiplication, I can always multiply the names as well. Milliliters times milligrams is milliliters times milligrams. And then I'm going to divide by the 5 milligrams. So I have 100 divided by 5 is 20. The milligrams divide out, leaving us with milliliters. So the units do work out as well in the math. So if we are ordered to give to administer 1,000 milligrams. Our label says 400 milligram tablets. In your notes, use the proportion method to figure out what we're going to administer to the patient quick. So, what goes in our first ratio? Label is 400 milligrams per tablet, per tab. In our second ratio, 1,000 milligrams goes on top, tablets on bottom. Cross, multiply, and divide. 1 times 1,000 is 1,000. Divided by 400 is 2.5. So 2.5 tablets we would administer to the patient. Or let's say we've got an order to administer 400 milligrams to the patient, and our label states it is constituted to 50 milligrams in 4 milliliters of solution. Again, go through quick and use the proportion method to find how much to administer to the patient. So for our first ratio, we use the label, 50 milligrams, 4 milliliters. In the other ratio, the milligrams have to go on top. So 400 milligrams on top, milliliters on bottom. Cross, multiply, and divide. 4 times 400 divided by 50 is going to give us 32. So administer 32 milliliters to the patient. Our last method is dimensional analysis. Dimensional analysis starts with the doctor's orders and proceeds through to what you're going to administer to the patient. It uses the label as a conversion factor. In other words, I'm basically doing just a unit conversion. I'm going to give you an example of dimensional analysis outside of medicine quick, so that you can see how this works. Let's say you need to travel 400 miles. You're going to have an average speed of 50 miles per hour. Find the time it's going to take to make that trip. Well, we are starting with the desired 400 miles. I'm going to make it a fraction by putting it over 1. So 400 miles over 1. I am going to use my average speed of 50 miles per hour to convert it. Now, when I'm doing a unit conversion, I'm getting rid of one unit and changing it to another. So I have miles, so that means I'm probably going to be getting rid of miles and changing it to what I'm trying to find. Well, I'm trying to find time. Hours would be time, so changing it into hours does work. So what that means is over here I'm going to put miles on bottom and hours on top. This rate here, 50 miles per hour, is actually a conversion factor. It can be thought of as saying 50 miles equals 1 hour. That'd be the same as saying 1 foot equals 12 inches. or 1 cup equals 8 fluid ounces. It's a conversion factor. So over here, I can put in 50 miles and 1 hour. So the miles will cross cancel out. 400 times 1 hour is 400 hours. 1 times 50 is 50. 400 hours divided by 50 is 8 hours. It'll take 8 hours to make that trip. Now, most of us somewhere along the line just memorized it in a problem like this. You take your miles and you divide by your miles per hour. But the dimensional analysis here tells us how to do that. So now let's take that into a medical situation, where your doctor orders 400 milligrams of medication. The label tells us that it is constituted at, let's say that it is 20 milligrams in 3 milliliters. So we're going to start out with the doctor's orders. 400 milligrams. I'm going to make it a fraction by putting it over 1. So to do a unit conversion, again, I'm getting rid of an original unit and changing it to something else. This is in milligrams, so it implies I'm going to have to get rid of milligrams. So milligrams go on bottom here, so that when I do my calculation, they will cross cancel out. Do I have a relationship between milligrams and anything else? Well, I'm using my label to do my conversion factor. So in my label, does it state a relationship between milligrams and anything else? Yeah, milligrams and milliliters. It is saying 20 milligrams in 3 milliliters. So as I said, my milligrams cross cancel. I have 400 times 3 milliliters is 1,200 milliliters. 1 times 20 is 20. I divide that out to get 60 milliliters. 1,200 milliliters divided by 20 is 60 milliliters. The big thing I like about this dimensional analysis is, like I said, 90 to 95% of our problems can be solved with dimensional analysis. Dimensional analysis can be done multiple steps all at once, or you can separate it out and do 1 step at a time. What we've done here so far are all 1-step problems. We're going from 1 unit into 1 other unit. We don't have multiple steps. We're not looking at something when we get into IV flow rates, where we might be going from milligrams per hour and having to change that into things like milliliter per minute or drops per minute. There might be 3, 4, or 5 steps in that conversion. If we were using the dosage calculation formula, we would have to use that formula for 3, 4, or 5 times. Or we'd have to do some unit conversions first, where we'd be using dimensional analysis anyway. And then it's somewhere along in the middle of that process, use the dosage calculation formula. Let's look at one more example here before we hang her up for the day. So let's say our doctor orders 1,500 milligrams. Our label is 400 milligram tablets. Just like before. Start out 1,500 milligrams. Make it a fraction by putting it over 1. In our conversion factor here, what has to go on bottom? What units? Milligrams. Because we have milligrams here, we must have milligrams on bottom here, so they cancel out. Our label says 400 milligrams per tablet, or in a tablet. So what goes above it is 1 tablet. If you want to refer back to our dosage calculation formula, basically this is the on-hand dose on bottom, and this is the vehicle on top. So the milligrams divide out. 1,500 times 1 tablet is 1,500 tablets. 1 times 400 is 400. We divide that out to get 3.75 tablets. We'll leave that up to a different discussion as to whether you round that to 3.5 or to 4. Fortunately, in math world, we can have 3 3/4, and we don't care. So for next time, homework that covers what we've discussed. There's page 146, covers our solutions. I know we didn't specifically discuss it, but on page 153 to 154, it goes through some different notations and different labels that use those abbreviations. I'm not going to require that one, but it's something you might want to look over on your own just to be familiar with it. Make sure that you can understand those labels, because at some point you're going to need to be able to do that, not for this course, but for your programs. Page 162 to 163 is that dosage calculation formula. Feel free to play around with those and try some of them with the proportion and some of them with the dimensional analysis, just to see which method works best for you. Like I said, I am a strong supporter of dimensional analysis. I'm not going to force anybody to do it either way, but I'm going to push you a little bit towards dimensional analysis. But come next week, I'm going to ask you guys what method you prefer me to use when we're doing problems. And so I'll try to do them, the methods that fit what you guys prefer the best. And then the last page, 168 to 169, deals with dosage calculations and with those stringents. Okay, well that is it for this week. You guys have a great week. Remember, we have lecture next week. 2 weeks from today is our Unit 3 test. And as I mentioned, we'll take the whole 2 hours for the Unit 3 test. You guys have a great weekend.